All right, let's talk about the ultimate cheat codes for calculus, differentiation rules. Seriously, these are the shortcuts that are going to save you from pages and pages of tedious algebra and let you find the rate of change for pretty much any function out there. Let's dive in.
I mean, have you ever been there, just lost in a sea of algebra, trying to use that long limit definition of a derivative? You know the struggle. It's fundamental, yeah, but let's be honest, it is not the fastest way to get things done. The good news? There is a much, much better way, and we're about to learn it.
And here it is, the infamous limit definition. This is the foundation of all of differential calculus. But as you can see, it's not exactly user-friendly, is it? Trying to find the derivative of a simple function, say x cubed, with this formula, it can be a total nightmare. And that's exactly why we're going to build a toolkit of rules to make our lives way easier. So here's our roadmap. We're going to start by quickly looking at the problem we're solving. Then we'll build up our toolkit, piece by piece, starting with the absolute basics. From there, we'll move on to some more advanced techniques. By the end of this, you'll see just how much these rules can completely transform how you do calculus. Okay, to really truly appreciate how awesome these rules are, we first have to remember what we're trying to avoid. Finding the derivative of x cubed with that limit definition is such a long, messy process, right? You're expanding, canceling, factoring. It's a real headache. Well, we're about to find the cure. Let's start with the two most fundamental rules in our whole toolkit. Think of these as the building blocks that will let us differentiate any polynomial super easily. This is where the magic really begins. First up, the constant rule. Now this one just makes sense logically. Think about it. A constant function, like y equals 5, is just a flat horizontal line. And what's the slope of a horizontal line? It's 0. Since the derivative is the slope, it makes perfect sense that the derivative of any constant is always 0. Simple, elegant. So for example, if your function is just f of x equals 8, its derivative, f prime of x, is simply 0. And it doesn't matter if that constant is 8, or -3, or even pi. The derivative is always going to be 0. And now for the power rule. This is a true game changer in calculus. It's a super simple two-step process that will save you so much time. All you do is bring the exponent down in front as a coefficient, and then you just subtract 1 from the original exponent. That's it. It's really that easy. Let's try 1. If we have f of x equals x to the 10th power, we just bring that 10 down to the front and then subtract 1 from the exponent. And boom, that gives us 10x to the 9th. See how fast that was? Way better than the limit definition. Okay, so now we've got the constant rule and the power rule in our back pocket. Let's see how we can combine them to tackle more complex functions, like polynomials that have multiple terms. These next three rules are great because they work exactly how you'd intuitively hope they do. The sum and difference rules basically just say you can differentiate a function one term at a time. And the constant multiple rule, it just means that if a term is being multiplied by a number, that number just kind of chills out in front while you differentiate the rest of it. Let's walk through an example to see all of this in action. For the function 2x to the 5th plus 7, we can use the sum rule to break it apart. First, the derivative of 7 is just 0. That's our constant rule. For the 2x to the 5th part, that 2 just hangs out in front, and we use the power rule on x to the 5th, which gives us 5x to the 4th. Finally, we just multiply that 2 and the 5x to the 4th to get our answer, 10x to the 4th. See? We just layered the rules together. So we've totally mastered polynomials, but what about functions that are multiplied together or divided? For those, we're going to need a new set of tools. They're a little more involved, I'll admit, but they open up a whole new world of functions we can differentiate. Now, before I even show you the rule, let's talk about why we need it. It's so tempting to think that the derivative of a product is just the product of the derivatives. But check this out. We already know the derivative of x squared is 2x, right? But if you try to differentiate x and x separately and then multiply them, you get 1 times 1, which is just 1. Those are not equal. So this is a huge takeaway. You need a special rule for products. And here it is, the product rule. Now, it might look a little complicated at first glance, but there's a really simple pattern. It's just the derivative of the first function times the second one left alone, plus the derivative of the second function times the first one left alone. So let's try it out on this example. First, we find the derivatives of our two pieces. The derivative of x squared plus 2 is just 2x. And the derivative of 3x cubed minus 5x is 9x squared minus 5. Then we just plug all those pieces into the product rule formula. Done.
Okay, now for the quotient rule, which is what we use when functions are divided. The formula is a bit of a mouthful, so a lot of people use a little rhyme to remember it. Low d high minus high d low, square the bottom, and away we go. Here, low is the denominator, high is the numerator, and d just means the derivative of. Let's use that quotient rule here. We identify our high function, which is the numerator, and our low function, the denominator. We find their derivatives, and then we just plug everything into that low d high minus high d low formula. It's really just a plug-and-chug process once you know the rule. We've done it. We've assembled our complete toolkit of differentiation rules. So now let's really put them to the test on a problem that would be an absolute nightmare to try and solve with the old limit definition. You know, a good rule of thumb for these is to apply the rules in the reverse order of operations. So this function, overall, is a quotient, right? A fraction. So we start with the quotient rule. But to find the derivative of that numerator, we actually need the product rule. And inside that, we need the power rule. You just work from the outside in, applying the right tool for each job at each step. So we've learned the mechanics of all these rules, but what can we actually do with them? Why does this matter? Let's check out a couple of real-world applications to see just how powerful these tools really are. A classic calculus problem, finding the equation of a tangent line. With our new rules, this is an absolute breeze. First, we find the derivative of the function. That gives us a formula for the slope anywhere on the curve. Then we plug in our x value, in this case 1, to find the specific slope at that exact point. Finally, we just use the good old point-slope formula to write the equation of the line. Simple as that. And of course, derivatives are absolutely essential in physics. If you have a function that describes an object's position over time, its derivative is its velocity. So in this example, we'd use the quotient rule to find the velocity function. And then just plug in t equals 0 to find the velocity right at the start. These rules give us a direct link between position and velocity. It's incredibly powerful. So think about it. We started with that long, intimidating limit definition, and now we've built this entire toolkit that lets us find derivatives quickly, efficiently, and for all sorts of functions. We've seen how these rules work on their own and how they all work together, turning these abstract ideas into real, concrete tools for solving problems. The only question left is, what problems are you going to solve?